Hello Math 1325 students, let's begin Lesson 10. Implicit differentiation and related rates. The implicit differentiation is a differentiation that applies to implicit relations, such as this, or that, and here's a third example. In short, an equation of x and y put together. Sometimes we are lucky we can solve it with respect to y, and y equals to f of x form, and we have an explicit function, but in many cases we can't. Here's an example that we can't. This implicit relation gives rise to this curve, which calls implicit curves, and in this case the implicit curve is an ellipse. And of course, please note that it fails the vertical line test and horizontal line test too, so you cannot solve it with respect to y or x. Here's another example. This time it's a hyperbola. Interestingly, this time we have two curve pieces. Yes, that can happen for implicit curves. 2, 3, 4, whatever. Another example here, and curves can cross itself. All kind of things can happen. Okay, we went through some examples of implicit relations and implicit curves. But then again, what do they have anything to do with calculus? What about so-called implicit differentiation? Well, let's answer that question, but in order to do that, let us dig a little bit deeper into these implicit curves. Let's take a little bit different viewpoint, which we call the parameterization. And here's an example of a parameterization and parametric curve. Okay, we don't need this duplicate. Okay, here we go. Okay, here's an example of a parameterization of an implicit curve. And this red dot is moving around this green curve, and you can consider that original green curve as a trace of this red dot. So you can consider this red dot as the tip of a marker running on a whiteboard, and run it along, and what's left is a curve. And this dot is the parametric curve, and this green curve is the implicit curve, and they kind of look like this. So this equation, x squared over 9 plus y squared over 4 equals to 1, is this implicit curve. Now what is this x of t comma y of t? Well, you have some algebraic expression as well, but that's besides the point. What's really important is this x of t and y of t are a pair of functions with the independent variable t, which represents a time. And at the starting time, or when time is 0, elapsed time is 0 at starting position, x value is 3, y value is 0. And as time changes, x coordinate and y coordinate change. So x is the horizontal position and y is the vertical position. And this parametric curve, x of t comma y of t, put those two together. Oh, did I say something is changing? Well, whenever something is changing, you can consider the rate of change. And that's where the calculus is coming into play. So if you have this x of t, you can consider the derivative and you get x prime of t, and same goes to y of t, becoming y prime of t. We can consider the derivatives, the horizontal rate of change x prime and vertical rate of change y prime, and then they are related to each other. They are not going everywhere. This point x comma t y x of t comma y of t, this point that's confined along this curve, along this implicit curve, along this implicit relation. So x and y are related with respect to this equation here, and the derivatives x prime and y prime will be related a certain level as well. Exactly how? Well, that's something we're going to discuss a bit later. At this moment, let's just establish those concepts. So let's suppose we have an implicit curve, and somehow we can parameterize it as x of t comma y of t and get a parametric function, this red dot. Then you can imagine the moving dot model, and consequently you can consider the rate of change, rate of change, x prime of t and y prime of t. And they're related to each other somehow. Here's another example. This time, the hyperbola. Again, we don't need this duplicate anymore. And here we go. This time we have two curved pieces, so we ended up with two pairs of functions, x1, y1, first pair, and x2, y2, second pair. And horizontal and vertical position of the first dot, and the horizontal and vertical position of the second dot. And how are they algebraically related? It's pretty obvious, right? By symmetry, x1 should be negative of x2, and y1 and y2 should be the same. Anyway, that and a lot of other relations. Not a lot of other relations, as a matter of fact, just two more. One is the relation between x and y, this purple, and another one, the relations between x prime and y prime. That's how they are related. That's why we call those related rates. Let's see, do we have enough time for another visualization? Okay, here we go. Okay, one more visualization, partly for fun. Okay, there you go. In this example, the curve is crossing itself. Did I give you the analogy of the tip of the marker moving along a certain whiteboard? Well, certainly you can cross yourself. And the trace of that moving marker is a curve. And horizontal and vertical position of the moving marker is x of t comma y of t respectively. How to find those x of t and y of t, those are very different issue. It's possible, as we have in these t expressions, but that's not what we are up to here. All right, what are we up to then? Looks like that's something we should answer in the next video. See you soon.